Hello guys, my name is Shivam Pandey and you are watching me on Discover and Uncover YouTube channel. Yesterday we have covered the topic, the various the data organization methods like linked list, array, stack, queue, and different things in a data structure. And in today's lecture, we are going to cover the algorithms which are there in the data structures. Correct. So before proceeding, we have to know that what is an algorithm, right? So basically, an algorithm is a sequence of computational steps that transforms input into output. So these are the algorithms, right? So in very easier or simpler words, I can say that एल्गोरिदम वो होते हैं जो कि इनपुट को लेकर आउटपुट दें। ठीक है। अगर मैंने कोई इनपुट लिया, जैसे सपोज दैट मैंने अ, आपसे पैसे लिए, तो मैं उस पैसे के बदले आपको कुछ दूंगा ना। अगर आप किसी शॉप पे जाते हो कोई सामान खरीदने के लिए, तो आप मुझे एज अ पैसा एज अ इनपुट पे करते हो, और मुझे कोई और वो शॉपकीपर आपको कोई सामान एज अ आउटपुट देता है। ठीक है। तो ये एक बेसिक एग्जांपल है इनपुट आउटपुट का। ठीक है। और जैसे कि मान लीजिए कोई मशीन है, आप उसमें कोई इनपुट देते हो अपने कंप्यूटर के थ्रू या फिर कोई कीपैड के थ्रू। लाइक आपने टाइप किया THOUGH, ठीक है, आपने ये टाइप किया, तो वो जो डिस्प्ले होगा आपके स्क्रीन पे वो होगा आउटपुट, और जो आपने टाइप किया कीबोर्ड पे वो होगा आपका इनपुट। करेक्ट। सो प्रोसीडिंग, एल्गोरिदम्स के कैरेक्टरिस्टिक्स क्या होते हैं और क्राइटेरिया क्या होते हैं। मैंने जो बताया बेसिक क्राइटेरिया क्या है, इनपुट और आउटपुट, राइट, एंड फाइनाइटनेस, डेफिनेटनेस एंड इफेक्टिवनेस। इनपुट आउटपुट तो आपको पता चल गया होगा कि इनपुट आउटपुट क्या है। नाउ व्हाट इज फाइनाइटनेस? नाउ फाइनाइटनेस इज नथिंग बट अ थिंग which we can calculate or evaluate, right? And if any thing is finite, then we can definitely measure it and we can have our things on that. And if things are definite, we can see that the input output system works for that. And if the system is effective for it, we can just draw them and we can make them. Yeah, so finiteness is an algorithm must be terminate after finite number of steps. Yeah, so for if any system is infinite, then we can't find an end for it. Yeah. So we have to find a finite number of terminating steps so that we can end the system. Now, for definiteness, we have algorithm must be easy to understand and free of ambiguity. So the algorithms must be easy to understand for a common man also, that he so that he can read the algorithm and he can just know that what is happening in the system. Effectiveness is the algorithm must be effective. So it has to make some sense, right? And if an algorithm is not making some sense, then it is not right. So the algorithm has to make some sense, and it has to be finite. Input output should be there, and definite things should be there in the algorithm. Yeah. Moving ahead, we have performance measurement or measurement of efficiency of algorithms. To determine which algorithm is more efficient in comparison to another, we analyze the algorithm. Analysis of algorithm provides information how much time and how much space is required, and therefore the efficiency of an algorithm depends upon two criteria: time complexity and space complexity. Here it is being stating that the algorithms mainly depend upon two things: the time complexity and space complexity. So basically, here in the world of technology and coding, we have time complexity and space complexity of each and every code which exists in the real world. Because if time complexity is not existing, we can't know that how much time or space the program will take to execute its operations. So now let us see that what is time complexity. So you don't have to worry much about this. You have to only look upon the first line. The time complexity of a program is the time required to run the program, right? So it denotes the time requirement of that program to be executed in the system. So there are three possible cases related with the time complexity. These cases are best case complexity, worst case, and the average case. Right. So if our system is taking the best case complexity, then it says that the system is very much efficient and it is taking the minimum number or minimum time to execute its operation. If the average case complexity situation is reached or it is being executed in the system, it means that the system is not very much efficient or very much worse. It is in between the worst and the best scenario. Right, and if the system is taking a worst case complexity, then the time consumed by the system is very long than the expected time. So this is the case of the worst case complexity. These are the points written of the best case, worst case, and average case, which I have already explained to you. And you can take the help of these points to just write some points in your exams, right? Uh, for example, we have been given an array. Searching for eight data element would be best because the eight element is the first element of this array. So if we begin searching in this array, then if we try to begin searching, then we reach the zeroth element or the first element of this array at the beginning itself. And if we find the eight at this place only, then we will take the minimum time to reach this to search that element. And if we have to if we have to find four, then it is the last element of the array. Then we have to traverse one, two, three, four, five, and we have to reach the sixth element to find the element four. Right? So it will take a lot of time, and it will be the worst case for that algorithm to find that number four. And if we have the average case, then we have to find the numbers between 8 to 4, which are 1, 2, 5, and 3. That will take the average case, which is not very much higher time required, and not very low time required by the system. Yeah, so moving ahead, we have cache performance like row measure and column measure order. So we have been given a matrix I can say, order of row or column, which is being denoted by a 3 cross 3 matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the nine elements present in this matrix. And if we have to denote it in a row measure order, then we have to write it in an order where we have to firstly write the first row, second row, and the third row. Right. So this is the first row, this is the second row, and this is the third row. So if we have to denote it in the row major column, then we have to do one thing, that we have to write the first row first, second row second, and the third row third. Simultaneously, we can write this in a particular sequence to arrange this in a row major order. So we have been given this example 1, 2, 3, 4, 5, 6, and 7, 8, 9. And if we have to write it in a column major order, then we have to write 1, 4, 7, 2, 5, 8, and 3, 6, 9. Yeah, so this is the column major order. We have also been given two codes. The code number one is denoting for I equal to 0 to I equal to n, sorry, I less than n, and I plus plus. Okay, so we have been given two codes, code number one and code number two, which are basically denoting the sum of this whole matrix, right? So I think so that here we are comparing something, some points. Basically, okay, so I got it. Here we are discussing that which will take more time to execute the code. I think so. The code number one will take lesser amount of time than code number two because the code starts from I equal to 0. And if a and in the C language, the code starting from I equal to 0 is considered as default, and it takes lesser amount of time than for the code starting with J equal to 0. This will also run and this will also run. There will be no difference in the result of this or the output of these both codes. The result or the changes which will be there will be internally in the system. The second code will take more time because it is starting from j equal to 0. So our computer has a fixed like a computational system where it takes input from I to 0, I0 to IN first, and then from J to JN. Uh, in the code 2, we have reversed the order, and then we have tried to solve the question. So it will definitely take more time, and the cache performance will be worse in the second case, right? And here we have been given a virtual memory performance. A part of hard disk is reserved by operating system as an extension of main memory. This is known as swap space. Yeah. So you all know about virtual memory performance, or you all know that what a hard disk is and what an operating system is. So hard disk is the total memory of your computer, which is which is put up by the manufacturer of the your laptop or PC or anything you use, and it is fixed in size. It is fixed by the company, and you use that hard disk to store things, to have your anything you want in your system. So it is an virtual memory uh, which is stored in your system, right? So also we sometimes use the also technologies have been made so that we can use the hard disk memory to extend the RAM. Some in some mobile phones, or you can see in your Android phones that extension of RAM is available in the settings, which means if you have a phone of 8 GB, you can extend it to 16 GB or so by using your hard disk memory, and using that memory to increase the limit or the increase the size of your RAM, which is almost non-expandable if you like try to expand it by some external memory, which is not possible. But companies are giving features which you can do by yourself by just clicking upon some buttons in the system. Now coming upon the difference between the fundamental operations and the non-fundamental operations. Fundamental operations have constant time, they have non-constant time. It requires only one data item, it requires multiple atom or a sequence of atoms. In fundamental operations, we can do add, multiply, division, load, store, output. And non-fundamental, we have array, string, vector, matrix multiplication, anything. Yeah, so a basic example is given over here. We have A equal to 5, B equal to 10. In C, we are adding A plus B, which will give us an output of 15, and the time complexity will be big of 1. Because here in this code, any loop or something like that is not running, right? So it is almost taking like in this code you can just easily see that we are not doing some multiple steps, some for loop, some while loop. We are not using them, right? So it will take the a minimum time, or we can say a constant time, which we denote as one in the system, and we take the complexity as big O of one. In the second, you can see that we have a array of 200 space, and we are printing percentage SS. Okay, so we are trying to just print this whole array of 200. So if we are trying to print it, then it will not be printed like this manner. As this code is incomplete, and we will require a for loop which will traverse the loop from I equal to 0 to I less than n I plus plus. So we require that line over this print line, so that we can print this whole array of S, and the time complexity for this array will be omega big O of n, because it requires the line. Okay. So coming upon the asymptotic notations. So, asymptotic notations are used to describe the running time of the algorithm. It describes algorithm as efficiency and performance in a meaningful way. Sorry, it would be way. We have written wave. Sorry, it is a typo in the PDF. I will correct it soon, and we will share the notes again with you. Is asymptotic notations are the mathematical presentation of time complexity. Okay, we have three asymptotic notations, or like we have big O notation, omega notation, and the theta notation. So I have described you about what worst, best, and the average case is uh, in the time complexity. So we have been given some symbols which denote the worst, best, and the average case complexities. The worst case is denoted by the big O notation, the best by omega notation, and the average by the theta notation. So you can see the symbols here like O and omega and theta from here itself. And coming upon to the big O notation, it is used to define the worst case, and we have the upper bound of an algorithm running time for non-negative functions fn and gn if there exists n naught and constant c greater than 0, such that for all integers n greater than n naught, fn should be less than equal to c dot gn. Then we say that the fn is big O of gn. It is denoted by, so here is a graph, and you can see this graph. Right. So you must be wondering that what is this function written over here. So I am really sorry that I do not have one pen supported in my system. If pen would be there, then it would be very much easier for me to demonstrate you, or to like teach you, like just using a class board, or like something official like that, whiteboard something. I'm really sorry for that. I have to use this pen of my system only to guide you. So I'm trying to just pick up on some. Yeah, no, it is quite very uh, just a second, guys. Just a second. Yeah, yeah. So what is Fn? Fn is function of n and less than c dot g n. Yeah. So you must be wondering that what is this? Yeah. So now let us see that what is this. So this is nothing but a function. Fn would be always given to you in your question. If you are saying any question, then Fn would be given to you. For let us say this example, and we have Fn here at 2n square plus n with the time taken by any problem. We have to write the function Fn as form bigger. Okay. So for any function Fn equal to 2n square plus n, you have to find this c dot g n. So what is Gn? So basically by hit and try method, you have to find a function which is greater than this 2n square plus n. So if we see that we take the Gn as n in the starting, then 2n square, we don't take n or 2 in the starting, we only take the n square. We compare with the n square. So n square is, if we take Gn as n, here if we take n, then you can easily compare and see that n is lesser than n square. It is very much obvious, right? And if you take n square, and we also take n square over here, then there is a comparison which is acceptable, or I think so, which would be healthier here. Yeah, so if we have n square here also and n square here also, then it would be easier for us to compare, and there would be a comparison between those elements, right? So if we take 2n square, we have to find a number function which has to be greater than this number. So let's suppose we take 2n square here also. Then these two systems will not be equal, but the 2n square plus 1 would be more, or I can say would be greater than the 2n square here. So we have to take a bigger number than 2 for the constant number to have a number which is greater than the 2n square plus n. So we take the number as 3, and by 10 12, if we try to compare it with, if we take here 1, then we have 2 into 1, which is 1, 2 plus 1, which becomes 3. And if we take here also 1, we get like 3, which is both are equal, and we don't have any problem here because we have equal to or less than sign here. So if the numbers are getting equal, then we don't have any problem. So we take a bigger number to compare with. Okay, so we are taking a number of let's suppose 3. So 2 into 3 square, which is 9 into 2, 18 plus 3, 21. Okay, we are getting 21 here. And here we take 3 square, which is 9, and 3, 27. So 27 is greater here. So our 3 n square is the perfect solution for this equation. Sorry, guys. Proceeding, if we try to solve this equation, it is very much basic math. If we try to solve this, then we solve it like this, and we get a value of n greater than equal to 0 or n greater than equal to 1. So we get two solutions for the equation: n not equal to 0, n not equal to 1, or n not equal to yeah. So we only get three equations. This one is not like the equation which we have taken from this. We have two equations, this and this, from the above solved equation, and you can use it to show in your paper, and you can draw this when you have found the c and the gn function which we require, and we have, and this is the way to represent this gn function fn equal to omega of gn, which is n square. Yeah, so this is a very basic way to find out the gn function from your given big omega function. Big O, big O notation. Sorry, not big O, but big O notation. Right. And proceeding with the big omega notation, so it represents the lower bound or the worst case scenario of any situation. So we reverse the comparison sign, and we take fn greater than equal to c dot gn. And similarly, here also this is the graph, and we have to find the same things that we did in before. And theta notation. Theta notation, we have the middle of the best and the worst case. So this comes in between these two cases, and in the function also you can clearly see that fn comes in between the c dot gn and c1 dot gn. So here we have our function fn, which is less than equal to c2 dot gn and greater than equal to c1 dot gn. So the way I have explained you the big O notation, similarly you can find out this gn function from here. Basically, gn function would be same in both the sides. The only difference which you would get in the where that you would get is the C1 and the C2. So the constant will change in both sides. For example, if we have 2n square as a function here, then we will get 3 into the place of C2, and we will get 1 in the place of C1, or 2 would be also, I think so, like not very bad option. Or you can use one also here or two also here. That depends on your wish and your things. Coming upon the time and space trade-off. Space and time trade-off is basically a situation where either efficiency can be achieved or at the cost of time, or time efficiency can be achieved at the cost of memory. Right. So let us take one example. If we are having one compressed data file, a compressed data file is a file, if you don't know, like zip file, where we have the whole file in a compressed manner, in a less storage, or in a reduced data file size. Yeah. So if we have that file, then it would be very much efficient for the system to store that file because it is taking less space. But if we try to open that file, the problem will come at the time when we have to decompress the file, because it will take the same amount of time to decompress the file, and then only it will open the file. So this compression solves the problem of data size, but it increases the time taken to open the file. So in simple words, I can say that time complexity or space complexity दोनों एक साथ अचीव करना पॉसिबल नहीं है टाइम पे। ऑल्दो ऐसे सिस्टम एग्जिस्ट कर सकते हैं जहां पर दोनों एफिशिएंसी अचीव हुए हैं या हो सकते हैं, but they are like very ideal systems, and we cannot just rely on those systems, because in normal day-to-day life or in practical life we do not have some systems. So this is the key concept before the time and space trade-off. And if you get this type of question in your exams, then you will get this question in, I think so, 7 marks in negative, and you can almost write write about 2 to 3 pages for this. You can take various examples, like how we are, like in different situations, how time is being compromised and space is being reduced, and how in some situations you can prove that space is very large and time complexity is very much less. So you can take examples and you can explain it in your own words. If the concept before any topic is clear in your mind, then you can write the points without thinking or without remembering or without just memorizing them. You can write the answer in your own words, and you can write as much as much as possible in your answer sheets, right? So coming upon example of calculation of time complexity. We have studied the time complexity. Let's see that how we can calculate the time complexity of different functions of different codes. Like for always remember that for codes which have the for function. For functions mean what? We are making a loop which is going from I equal to 0 to I equal to n, or anything I less than n, or I equal to n, anything it can be there. But you have to see one thing, that we are starting from a place which is I equal to 1, I equal to 0. Then we are moving to I equal to 1. Then we are going to I equal to 2. Then we are going to I equal to 3, till we are reaching I equal to n. So you see one thing, that we are doing the steps, or we are just doing the same thing again and again up to a number n, and we don't know the end point of this code, right? So we take the complexity, or we take the time complexity for this code as n, right? Because we are running this code n times, so we are taking the complexity of this code as omega, or big O of n. Sorry, I'm taking omega name again and again. Omega is not the correct word you have to use here. Big on, because we have to always calculate the worst case, not the best case. So we have taken omega of n, which you can see here, right? So we have a code which is from I equal to n to I greater than 0. So it is basically a decrement code. We are coming from a higher number to a lower number. Again, it will not be a difficult one. You all know that the time complexity for this one would be also omega of n. Omega of n, not big O of n. Sorry for that mistake. And the third question is that we have to find the time complexity of I equal to 0 to I less than n, I plus 2. Uh, some people might be thinking that is running from uh, this is running half the time, so so the time complexity will be reduced. This is not the case. The time complexity will not change, but it would remain the same as big O of n. If we have two loops, then you can imagine in your mind that the code is running from I equal to 0 to I less than n one time, and for j it is also running once again. So we are getting the same code running for two times, and if the things are overlapping, the things are getting twice or increasing, then the almost the time complexity is getting uh, like enhancing or increasing, and we have a time complexity of n square, because this has a complexity of n, and this has complexity of n, and we are not and we are doing operation where we are performing these two operations at the same time. So we multiply these two and we get n square here. Right. So coming upon this, I equal to 0. This will also be this the complexity is n, and here also it is n. Then if we multiply them, then we will get n square. I think that would be a much difficult for you all to solve this. Uh, yeah, so time complexity equal to log 2 of n. So examples are given over here, and we have a formula to solve this log n property. If you know the formula of log n, then you can solve this by your own. And I think so that it is a simple formula that if you are having 1, then you have to take this as n by 2. If we have 2, then you can take n upon 2 square, which is 4. We have 3, then you can take 2 cube, which is 8. So it is very much basic, and general formula is given over here for k times. You can use this and find out the required things. Now, complexity of this code binary search. I think so that most of you are not aware of this searching and sorting techniques, which is there in your second or I think so third unit in your data structure in your AKTU. But at this time, at this level of knowledge, we have to only look upon the number of uh, loops in this code. The first is the while loop. Then you are saying one this if statement, which would again check things. This would take a complexity of n, or big O of n. Again, you are checking something, and yeah, you are getting your outputs like this. Yeah. So I'm not taking this like code to explain this to you now because you don't know the this code much and you might get confused. When we'll study the binary searching and where the different searching techniques like linear search and binary search, then definitely I will try to explain you this code at that time, and we will get the time also at that time to explain you this code and the time complexity and space complexity of this code. Here 3D matrix also given. You can easily find because it is n, it is n, and for k also it is n, and multiply them we get n cube. Yeah. On multiplying these three, this loop, and this loop, we get space complexity as omega big O of n cube. Okay, so for this lecture, we are keeping this much only, and we will continue in our next lecture with array and different things. We will see in the next lecture. We have almost completed 10 to 15% part of the unit 1. The unit 1 is the lengthiest part of your whole data structure syllabus. It is the lengthiest and the most longest unit of your syllabus. So it will take time to complete this thing, and we have not started for English yet, and we will require time for that, and we need more time for the completion of English and things like that because they are good topics and require more time and more support from you to just explain you things of English and the different queue stack which will come in your future. So that's all for this lecture. I hope you guys are revising things and you are going and you are doing good in your time. So that's all for now. Thank you and have a good day.